It's time for us to make a little more progress in our series of lessons on the application layer. This course is entitled Networks and Distributed Systems, based on the text by Jim Couros and Keith Ross, Computer Networking, a Top-Down Design. We left off in the last lesson talking about cookies. Let's pick up where we left off. This slide shows us how the process works. What we're going to see is that a user has accessed an Amazon server. The Amazon server checks the user's computer and sets a cookie to identify that user with in the future. The transaction is finished with a normal response message. Sometime later, the user accesses the site again. This time, however, the cookie is already there, so the server is able to identify the user, and a number of things are possible with this system. Cookies can be used to provide authorization of users. They may also be used to update shopping carts. Perhaps you have noticed that when you access Amazon or certain sites, it might show you some products related to things you bought in the past. So cookies allow that vendor to make recommendations. The question then is cookies and privacy. Cookies do allow a server to learn quite a bit about you. However, we know that we can delete those cookies off of our computer. Furthermore, we can set up our computer to refuse to accept those cookies. Now, some websites that you want to use require that they be able to update your cookie file. I'm not aware of any problems occurring as a result of this cookie file, but you have full control over it, so you can delete it if you want to. A web cache, also called a proxy server, is a network entity that satisfies HTTP requests on behalf of the origin web server. The web cache has its own storage and keeps copies of recently requested objects in storage. Once a browser is configured, each browser request for an object is first directed to the web cache. You notice there that the client sent a request to the proxy server for a page. Apparently that page did not exist in the proxy server, so it sent a request to the web server that the client was trying to access. The web server that the client was trying to access responded to the proxy server, which in turn responded to the client. The next time that client requested that page, the proxy server was able to satisfy that request without having to access that origin server, because it had stored a previous request for that page in its own storage. So we can see that a cache is both a server and a client at the same time. When it receives requests from and sends responses to a browser, it is a server. When it sends requests to and receives responses from the origin server, it's a client. Usually a web cache is purchased and installed by your ISP. A web cache can substantially reduce the response time for a client request. Also, web caches can substantially reduce traffic on an institution's access link to the internet. By reducing traffic, the institution does not have to upgrade bandwidth as quickly, therefore reducing cost. Furthermore, web caches can substantially reduce web traffic in the internet, thereby improving performance for all applications. However, as you can see, there's a problem. The link is swamped, 99% link utilization. Now granted, the improvement's just a matter of buying more bandwidth. However, the kind of increase we're needing here would be very expensive. Adding a local web cache would be significantly cheaper, and the performance would be even better. Here you see how the calculation can be done. Pause the video if you would like to study it closely. Although caching can reduce user-perceived response times, it introduces another problem. The copy of the object residing in the cache may be dated. In other words, the object housed in the web server may have been modified since the copy was cached at the client. Fortunately, HTTP has a mechanism that allows a cache to verify that its objects are up to date. This mechanism is called a conditional GET. An HTTP request message is a conditional GET message if the request message uses the GET method and the request message includes an if modified since header line. And you see how that request is made, and it's got the if modified since, and it's updated. To see how the conditional GET operates, let's walk through an example. First, on the behalf of the requesting browser, a proxy cache sends a request message to the web server with if modified since date in the header. If the data has not been modified since the date included in the if modified since method, it sends no data. We see that in response to the conditional GET, the web server still sends a response message, but does not include the requested object in the response message. Including the requested object would only waste bandwidth and increase user-perceived response time, particularly if the object is large. Note that this last response message has 304 not modified in the status line, which tells the cache that it can go ahead and forward its cached copy of the object to the requesting browser. This conditional GET is telling the server to send the object only if the object has been modified since the specified date. If the data has been modified since the date indicated, the origin server returns the updated data. This ends our discussion of HTTP, the first protocol, an application layer protocol, that we've studied in detail. We've seen the format of HTTP messages and the actions taken by the web client and server as these messages are sent and received. We've also studied a bit about the web's application infrastructure, including caches and cookies and back-end databases, all of which are tied in some way to the HTTP protocol. Now let's move on to another very popular and older application, File Transfer Protocol. FTP is an application that allows a user to transfer files to or from a remote host. To access the remote host, the user must provide a user identification and a password. After providing this authorization information, the user can transfer files from the local file system to the remote system and vice versa. The user first provides the host name to the remote host, calls an FTP client process in the local host to establish a TCP connection with the FTP server process in the remote host. The user then provides the user identification and password, which are sent over the TCP connection as part of the FTP commands. Once the server has authorized the user copies one or more files. HTTP and FTP are both file transfer protocols and have many common characteristics. For example, they both run on top of TCP. However, the two application layer protocols have some important differences. The most striking difference is that FTP uses two parallel TCP connections to transfer a file, the control connection and the data connection. The control connection is used for sending control information between the two hosts. Information such as the user identification, passwords, commands to change remote directory, commands to put or get files. The data connection is used to actually send a file. Because FTP uses a separate control connection, FTP is said to send its control information out of band. HTTP, as you recall, sends request and response header lines into the same TCP connection that carries the transferred file itself. For this reason, HTTP is said to send its control information in band. Here you see the simple commands used by FTP. Type in user and then your username, pass and then your pass name. List returns a directory or a list of files in that current directory. RETR, file name, retrieves the file. STOR, file name, stores the file. And over there on the right of the screen you see some sample FTP code. Well, we're about to start up electronic mail, so why don't we just stop right now and study your notes and your study guide and take care of any assignments that you may have. And when you're ready, come on back and we'll move on to electronic mail.